Grant Lewis,
Hi, Chris.
how's it going?
Pretty good. How about yourself?
I'm well. I'm well. So, Professor Grant Lewis of cosmology and book writing fame at the University of Sydney in Sydney, Australia. We actually know each other.
Yes, I think we wrote a book together, didn't we?
We did. Yeah,
We
that's
did.
right.
Yeah.
So the book is about is about the grand scale cosmology. Where did the universe come from, and where is it going?
Yes.
Uh,
Yes.
but today we're going to write a baby book, and it's as if it would fit into the series, which would include titles such as Bayesian Probability for Babies, which uh, often have kind of very unique and esoteric titles to attract the eye. And in this series, every book starts the same. So it starts with "This is a ball." These books are 24 pages, and mostly just a technical requirement for printing. But ends with sorry about the green screen. But ends with now whatever the topic. Uh, so today we're going to write Galactic Cannibalism for Babies, right?
Yep. Sounds a cool topic.
So where does that in where did the universe come from? In other cosmic questions, we kind of went from the beginning of the universe to the far future. Where does galactic cannibalism fit in? Because I don't think we didn't actually discuss that in the book, right?
No, no. So, galactic cannibalism is sort of the name that we give to the process by which big galaxies, like our Milky Way Galaxy, arose out of the featureless universe that existed after the Big Bang. So, universe was born, and it was mainly just a thin soup of gas spread throughout the universe. And here we are, 14 billion years later, and we find ourselves, orbiting the sun, but the sun is just one of roughly 200 to 300 billion stars in this object we call the Milky Way Galaxy, and there are between a few hundred billion and a trillion galaxies in the observable universe. So we want to know, how did the universe go from that featureless state to the rich structure that we see today? And what we have learned over time is that galaxies grow. So what you get is, soon after the Big Bang, matter started to be drawn together. You get the first stars in these little clumps, and then little clumps come together to create bigger clumps. And so you end up with a sort of bigger galaxy, bigger proto-galaxy. And things keep falling in, so smaller galaxies keep falling in, and as they fall in, they get shredded and dismembered, and their stars get added to the bigger galaxy. So the bigger galaxy continues to grow over time through cannibalizing smaller galaxies.
Right. Okay. So that I think that's a good galactic cannibalism for adults. Um, I don't think any of the books mention dismemberment, so maybe we won't we won't put dismemberment in. But I, so you mentioned the Milky Way, and what I didn't realize. So, of course, I saw stars when I was younger, and then at some point I learned about astronomy and cosmology, and you see astronomers and you read books about it. And you see photos from NASA of galaxies out there, and what I didn't realize until very late was we can only see with our eyes things in the Milky Way, right? We don't get to see stars outside of our galaxy.
Oh, yeah. There's a subtlety there. So we see individual stars inside the Milky Way. So when we look out in the night sky, there are roughly about 6,000 stars across the sky that your eye can pick up. So we can pick out those stars. But against those individual stars, you'll see there's the white smear of the thing we call the Milky Way Galaxy. And we know that that is the light of billions of stars basically smushed together across the sky. And we can pick out other galaxies from their smushed starlight. So here in the southern hemisphere, of course, we can see the Large and Small Magellanic Clouds. They are two small galaxies that are orbiting our Milky Way galaxy, and they are actually potential food for the Milky Way. It's likely to consume them in the future. But the most distant thing we can see with our naked eye is actually the Andromeda Galaxy. And if you know where to look, and it's one of those things that you catch out of the side of your eye, you can see a fuzzy blob, which is the heart of the Andromeda Galaxy, which is actually bigger than the Milky Way, and it's roughly 2 million light years away. So that's about as far as you can see. So not individual stars, but you can see the smush of starlight.
Okay, interesting. So Andromeda is bigger, and we're getting closer to it, right? Or it's getting closer to us, or well, it's symmetric.
Yes, we're falling towards each other, almost like a love story. Except, right. Do you remember a TV show called Heart to Heart? Back, you're far too young. Anyway, no. The opening the opening tagline was basically, and when they met, it was murder, right? It was one murder mystery. So these two big galaxies are heading towards each other, and they're heading for a collision. Right. So that's actually part of the overall galactic cannibalism picture. We normally call it cannibalism when a big galaxy eats a little galaxy, but now and again, big galaxies collide, and what will be left over from that collision will be a brand new galaxy. Right? So there'll be a bigger galaxy left over from the agglomeration of the Milky Way and Andromeda.
And what happens to the rest? Not all of the stuff that was contained in the original two galaxies is now forming a new galaxy, or
essentially,
stuff get just flung out.
So some stuff gets flung out because the collision can be can be very energetic, very violent, right? So some stuff does get sprayed out and escapes, but most of it, so the collision sort of happens and stuff gets sprayed out, but then falls back in again. And so you create this galaxy that's going to be left over that's going to have 1 trillion stars in it. So it'll be a big, chunky galaxy where these two individual galaxies used to be.
So Andromeda is a spiral, Milky Way is a spiral. Do we know what the merged galaxy will be?
We know that what it won't be. It won't be a spiral. Okay, so spiral galaxies, like our own Milky Way, they've managed to have that particular pattern because they've had a relatively quiet life, right? So in terms of collisions between galaxies, these bigger galaxies have just eaten smaller ones, and that's just made them put on a bit of weight. But in these big collisions between galaxies, then what happens is that the spiral structure all gets sort of disrupted and destroyed, and the stars all settle down into roughly a rugby ball shape. We call them elliptical galaxies because astronomers are really boring at naming things. So the beautiful disk structure is gone, and you're left basically with this big fuzzy blob of stars.
Okay. All right. All right. So I think I have a picture in my mind, an idea. I'm going to start to sketch out here the story. But it has to start with this is a ball. And in astronomy, it's easy because stars are ball shaped. So I think that the first few pages write themselves in that sense. The ball has to be a star. And then the story, I think, will be the story of that star in that galaxy. Now, I think history is written by the victor, so I think that star should be in the cannibalizing galaxy, not the cannibalized galaxy. And then maybe we can just tell that story of what that kind of star experiences. So if I'm like a star, and I'm happily sitting in my galaxy, and early on, I suppose the galaxies were small, and then they got bigger by cannibalizing other galaxies. Is that right?
Yes, that's basically it. Yeah. But that.
So how?
I think we had a small lag there. They grow bigger over time, and we know that a star like the Sun was probably born inside our Milky Way. So the Milky Way is probably 10 billion years old, but the Sun is only 5 billion years old. But what we don't know is where the Sun's parents came from, the stars that provided the material from which the Sun was born. So the previous generation of stars, they could have been brought in and lived their lives in the Milky Way, and then our Sun was born after they had lived out their lives.
Okay. All right. So it's not as simple as they're started with a few stars and then it slowly grew from a small community to a large galaxy.
Maybe for babies that picture's okay, but if you've got a proper astronomer reading it, they'd get a little bit grumpy.
Right. Well, life. There's a cycle of life, and it includes death. So I don't think that should be off the cards.
Okay.
So there's a ball. It's a star, and it's the stuff that it's made of came from other stars that lived out its life, and those stars came into the galaxy from somewhere else, although they themselves probably were born of older stars that lived out their lives. How many? What's a young star today? How many generations could it have been from?
Oh, nobody really knows, but we generally have what we call 3 populations. So we have the first generation of stars, which are rather annoyingly called population 3. And then we have the older generation of stars, which we call population 2. And we have the young generation of stars, which we call population 1. But in there will have been multiple cycles. So what you have to remember is that big stars live for a short period of time. So big stars will only live for 10 million years. Whereas stars like the Sun live for 10 billion years. And tiny stars, they can live for 1 trillion years, if not longer. So it's not like 70 years and 10. You've got some things that live their lives very quickly and other things that live their lives more slowly. And the generations is just this mix of all this stuff going on all the time.
Right. Okay. All right, I'm going to start to sketch some ideas. I'm gonna hide it from you, mostly so that you're not distracted by my terrible sketches. So you have like these multiple generations. What demarcates the generation? These 3 generations? Arbitrary?
For astronomers, it's normally where you find the stars. So in a galaxy like our Milky Way, we find the youngest stars in the disk because it's in the disk of the Milky Way that gas can get churned around and gets reprocessed into stars over and over again. So in the disk, we say, oh, there's population 1. In the center of the galaxy, where it's harder to make stars, that's where we tend to see the older population. So we basically say, oh, over there, they're older, and we'll call those population 2. And then out in the outskirts of the galaxy, which is where we find the oldest stars, well, again, my astronomer colleagues will, it's not as clean-cut as that, but that's where we tend to find the older stars. We call those population 3. But, it's one of those things that scientists like to do, right? We like to put things in boxes and then argue about where the edge of the box should be. And then after 100 years, we say, actually, there's no box at all. It's a continuum. So it's part of the process of how we've gotten to understand stars.
Kind of like Pluto.
Yes. Let's. It's.
Where are you on the Pluto? Where do you sit in the Pluto debate?
My position on Pluto is that what we call it is irrelevant. Because the definition that we came up with for what is a planet ended up being so convoluted that nobody really likes it, right? You want a nice, clean-cut thing of what is a planet. And it makes sense in the inner solar system where you have these distinct big objects and we say, those are the planets. But once we hit the outer solar system and suddenly see that, objects like Pluto and that you run into these trans-Neptunian objects and then into the Kuiper belt and all this kind of stuff. The labeling, it just makes things more complicated. So yeah, I'm going to say I don't really sit anywhere because I don't think it really helps.
All right, so I have an idea for how we can go from our friendly star. I have a star. It lives in a galaxy. It's a big galaxy, big spiral galaxy, let's say, like the Milky Way. And there's another smaller galaxy. Let's ignore Andromeda for now. There's another smaller galaxy, and they're approaching each other. So what happens when a galaxy like the Milky Way cannibalizes a smaller satellite galaxy?
We've got signs of this all over the sky, but one of the best known galaxies is a little guy called Sagittarius. So Sagittarius is a galaxy much smaller than the Milky Way, right? A few percent the size of the Milky Way. But for the last 4 to 6 billion years, it has been orbiting the Milky Way. And what happens is that, this little galaxy is a bunch of stars, but then as it falls into the Milky Way, the gravitational pull of the Milky Way across Sagittarius starts to stretch it and stretch it and stretch it. So it goes from being a rugby ball into more of a tube and then into a ribbon. And what we can see now is when we look out on the sky is we can see a stream of stars that completely wraps us around the Milky Way galaxy. So this is the debris that's been ripped off Sagittarius, okay, and now lies along this thing called a tidal stream. And at the moment, we can still see the main body of Sagittarius. So it's lost already a lot of mass, but we can see a clump which is still what we call the Sagittarius dwarf galaxy. But in a few more orbits, the action of the Milky Way's gravity is going to grind that object down till there'll just be a stream. And then after a while, that stream itself will disperse, and the signature of the existence of Sagittarius will be lost forever.
And the stars that were in there just become part of the arms of the Milky Way?
No, it depends on where the little galaxy falls in from. So Sagittarius, instead of orbiting in the disk, is orbiting over the pole of the galaxy. So its stars will disperse into like the fuzzy ball of stars, which we call it the stellar halo. So we have our disk and it's surrounded by this big, sort of very diffuse ball of stars which orbit at very large distances. And in fact, when we look out into our halo, it's like a stellar graveyard. We see the signs of lots of little objects which have been torn apart and are being torn apart by the Milky Way. So it's still a cannibal. It's still growing.
Okay, all right. How big in the Milky Way? How big is the? How should I picture it? I want to picture like a flying saucer. Is that the right sort of thing to be thinking about?
A flying saucer. Normally, what people say is more like a fried egg, because the disc is quite flat and then there's a bulge in the middle. So take 2 fried eggs back to back. So, but we used to have we used to have sweets, candy, or whatever, which we used to call UFOs, which looked like that. They were basically flat and then sort of bulged in the middle, and inside there was sherbet. So something like that.
Okay. All right. Was that in Wales?
Yes. Yeah. Had the best sweets in Wales.
Right. So was that was that one of the biggest culture shocks when you came to Australia? The difference in sweets?
I came to Australia, let's see, when I was almost 30, so I wasn't as into sweets as I was when I was a kid. The biggest culture shock is when I got to the US and I had to eat American candy and I realized I didn't like it very much. So everyone was going on about
really? Okay.
yeah, everyone's going on about Hershey bars, and nah, it's not real chocolate.
Oh yes. Well, yeah. The I mean that's not the most exotic candy you can find in America.
No, I know. Yeah, I was. I mean, I was in my mid-20s, so I wasn't going after all of the various things that you can find in America.
So, where's the best view of the Milky Way around the world?
Oh, Southern Hemisphere.
Where have you? Okay.
Yeah,
Right. Why
because
is that?
so our Milky Way, as I mentioned, bulges in the middle, but we are located out in the disk. So we are roughly 24,000 light years from the center of the galaxy. So when we look out from our vantage point, you can either look, outwards where there are less stars, or inwards where the center of the galaxy is. And the center of the galaxy is in the constellation of Sagittarius. So it's when we look on the night sky here in Australia, you get a really nice view of the center of the galaxy. If you look at the band of stars, it comes together and it actually gets broader, and kind of almost paradoxically, it gets darker, because towards the center of the galaxy, there's these big clouds of gas and dust which are blocking our view. But we know that in that direction is the center of the galaxy, and in there's a giant black hole, and there's lots of stuff going on there. So it's the exciting part of the galaxy for astronomers.
And we can see through this stuff with other wavelengths, right?
Yes. So the best wavelengths to use are radio waves. So Australia's got some big radio telescopes, and you can peer through the dust, and you can peer through the center of the galaxy, and you can actually see the spiral arms of the Milky Way out into the other side of the galaxy. So this is how we know how many spiral arms we have and where they are. And spiral arms are very important for a galaxy like the Milky Way, because those are the places where stars are born. Right? The reason that we see the spiral arms is because that's where there are lots of blue stars, and blue stars are hot stars, and hot stars are massive stars, and they're also young stars. So they're the places that stars are born.
So when I see so I've seen pictures of the Milky Way. If I Google it, I can find pictures. So clearly, they're not actual images. How accurate are these sort of like bird's eye view pictures of the Milky Way?
They're reasonably accurate. We know when we look at spiral galaxies, and we've observed, millions and millions of spiral galaxies. And again, astronomers like to classify them, right? So, and they classify them in terms of what their spiral structure looks like, how tight or loose the spiral arms are, or how big or small is that bulge of stars in the center. And there's another feature which is called the galactic bar. So they have other features. So from the observations that we've done, we know reasonably well where our Milky Way sits in this overall classification of spiral galaxies. So we can point to other spiral galaxies and say to ourselves reasonably confidently, if we could step outside the Milky Way and look back, this is what we would see. So yeah, there's been a lot of detective work to try and unravel the structure of the Milky Way.
And these pictures, they've changed over time, right? I think there was a recent one I saw that suggests that this is the most accurate picture we have now.
Yeah. So of course, what happens is that all of the time, our observational knowledge just gets better and better and better. And of course, it was only 100 years ago we didn't even know that there were other galaxies out there. We just thought that our sun was in this distribution of stars that went on forever. But over time, as we got new telescopes. So telescopes got bigger, which allows us to see further. And we were able to open other windows, right? So we have radio at one end, X-rays and gamma rays at the other end. They've allowed us to map out the Milky Way Galaxy. And essentially, whenever they say to you, oh, this is the new map of the Milky Way, what you tend to find is that the fine detail is now changing, right? So the overall picture we think is right, but exactly where the spiral arms are, so sometimes spiral arms break into two, and so where do these breaks happen, and just how much mass is there. These are things that we are trying to work on now, but the overall picture that we live in this big spiral galaxy of a few 100 billion stars is pretty concrete.
And how many spiral arms are there?
That's a good question. I'm not sure I know off the top of my head. Let's say, I think it's something like roughly eight. But again,
okay.
But
8.
Yeah.
Oh, okay.
But you have to be careful because it's not like 8 identical structures, right? There's a bit of messiness in there as well, and some spiral arms start in strange places, and I said other times spiral arms break apart. So yeah, it's kind of hard to find a nice simple spiral galaxy where you can just trace out the arms, because there tends to be a lot going on.
And when we see a photo from NASA or elsewhere of Andromeda, it is like a kind of elliptic shaped. Is that because we don't get the sort of perpendicular view of the disk? Is it actually circular?
Yes, yeah, we know it's quite. We know that the Andromeda. So Andromeda, when we look at it on the sky, as you said, is a kind of flattened kind of thing, but we've been able to measure the speeds of stars as they go around in Andromeda, and that tells us that if we could reorient the view, it would appear as a circular disk, but we don't see it from above. I mean, this is part of the problem. We're stuck here on Earth, and we have to live with the view that we've been given. And now and again, we do see spirals from the top, and we do see that they look nice and circular, but many of them are edge-on, so we just see them as thin lines, and most are, of course, at angle in between, so we see them just at various orientations.
Is there in our Milky Way we think is a circle? If I'm not mistaken, that's the latest picture I saw was fairly circular.
Yeah. So our sun goes around in an orbit, and that orbit basically traces out a circular path around the center of the galaxy. And it was actually slightly more complex than that. The sun actually bobs up and down out of the disk as it goes around. It's a bit like we call them merry-go-rounds in Britain. What do you call them? A Ferris? No, Ferris wheels are.
Yeah.
No. Is it a merry-go-round? The horse that goes up and down as it goes around. Yeah. So that's the motion that the sun follows. Is it bobs up and down around in a circle as it travels around the Milky Way.
Yeah. Why?
Well, it's because if you think about it, the disk of the Milky Way has got lots of mass in it, right? So if you try and go like up or down with respect to the disk, there's a force that pulls you back in. So the sun, when it was born in a gas cloud that was already doing this kind of motion. So it's going around in a circle, but it's also, as it goes up out of the disk, it gets pulled back in. It goes below the disk, it gets pulled back in. So it does this little bobbing around as it travels.
Oh, like, yeah, okay, yeah, I get it.
Yeah, and
sort of like a spring,
yeah,
up and down as it goes.
Absolutely, and in fact, some people have suggested that motion as we go through, so like the midpoint back and forth, is one of the things that could be responsible for the deaths of the dinosaurs, because they're
okay. How's that work?
So we've got our sun and the planets, and then surrounding all of that, there's a thing called the Oort cloud, which is where all of the comets live. And when we go through like the midpoint of our journey through the disk, that Oort cloud gets shaken, and so these comets then fall into the inner solar system. And it's thought that this rain of comets, that one of them 64 million years ago struck the Earth, and that was what was responsible for killing the dinosaurs.
All right. Okay, so I'm almost done. Let me show you what I have so far, and you can tell me how accurate it is. All right, so let me bring it up. So here's what we have so far. This is a ball. Okay, so this is just a sketch. Probably should have had a black background, I suppose, with white. It's a star. It lives in our galaxy, so it's got some lots of little stars around it. But zoom out, and it's a big spiral galaxy. That galaxy has a satellite galaxy, so I guess this will be like a kind of little cloud, a small little cloud. And then that satellite galaxy stretches, so this cloud is going to stretch out, and it's going to stretch out more and more. So it's kind of I guess, is it, there's the question. Now, at this point, is it like a kind of like really diffuse sort of ring that goes around?
Oh, it'll be a very, it won't be diffuse, it'll be a very tight ring. So it'll be like a
Oh.
yeah. So it takes a long time for those stars to disperse away from the stream. So they tend to just follow the orbit, and they're all just follow, like a line of ants, right? They're all just following each other.
Right.
So you get this nice coherent path.
Ah, okay. All right. Okay, I like that. Okay. And then at some point they kind of just joins the dispersed blob. Okay.
Yep.
And then we have a bigger galaxy, and then the big sort of aha moment is that it ate the smaller galaxy, and now you know galactic cannibalism.
That's pretty cool. Yeah.
All right.
So my niece is gonna be 2 shortly, and I would definitely give her this book.
Really? Okay.
Yeah.
So, okay. All right. Well, now I'll have to spend a bit more time, getting the illustrations perfect. So in the end, we should have this sort of pancake shaped thing of lots of little points of light surrounding this galaxy.
Mm-hmm.
Right?
Yeah. Yeah.
Okay.
So,
yeah. Okay.
I mean, you may not want
All right.
you may not want to use the phrase stellar graveyard, because that is not, but that's what essentially where many of these galaxies that fall in end up, is their stars are added to the overall sort of smush of stars we have around the Milky Way.
Right. Yeah. So I think what I would do is use a similar image to the beginning, and then just make it so that it's somewhat obviously has more points of light in
Yeah.
it. I think for most of these books, but not all of them, there's a book in the series called Astrophysics for Babies. It does have a dark background. Well, most of them are white backgrounds, really high contrast. But I guess with space-related things, it kind of necessitates a dark background.
Space is pretty dark.
I suppose I could just look at all of these photos from space in the negative, and that would suggest how to draw it with a white background. Is that right?
Yeah. Absolutely. I mean, there's no particular reason why you'd have to portray it as it actually is seen on the sky, right?
Right. All right. Now I have a slight sort of worry with this story here is that, especially at the end, um, the the images are tend to be a bit repetitive. So I'm wondering if there's something else that I could say at the end would, my worry about this last little spot here, like what it ate the smaller galaxy. What, how do you depict that without just repeating the last image, which just shows the galaxy that has actually eaten it? Or maybe there's something better you can say there. Like I do like the stellar graveyard, although again, what what gets drawn there? How do you illustrate that? So what is a concept, or what is a way to illustrate this concept, or what is a different concept that finishes off the story that can have a nice illustration?
You could suggest
What happens next?
yeah. Well, what happens next is that the next meal comes along, right? So there are other
Okay.
there are other galaxies out there, you know, almost waiting to fall in, right? So we have galaxies orbiting around, and they come in like an almost steady rain. And it's not like when the Milky Way is done with one, it gets its next one, but they come in, one here, one there, maybe a couple at a time, etc. So you could potentially zoom out and show the other smaller galaxies, the Milky Way is now waiting for its next feed.
uh, okay. So there are more smaller galaxies waiting to be eaten.
Yeah. That's basically what's
Okay.
happening. And part of my research now is looking at the populations of galaxies which are out there, which we sort of know are going to become food in the next several billion years. But on the time scale of the universe, that's not very long, right? So it's just all right. What's next? What's coming in?
And these small like satellite galaxies, they're just little blobs, right?
Yeah,
What are they called?
mostly. We call them dwarf spheroidals because most of them just look like blobs. But they do have structure as well. So one of the bigger ones is the Large Magellanic Cloud, which actually has like a disk-like structure in it. So it's a bigger galaxy, so it's gotten further along. And it turns out that there's another galaxy in what we call our local group, which is called Triangulum. And that's roughly a tenth the size of Andromeda, but it is a spiral galaxy, and one day it is going to come in and it's going to end up as food, probably for whatever is going to be here after Andromeda and the Milky Way have merged.
Okay, right. So the next major cannibalism event will be the merger of Andromeda and Milky Way, at least for us.
Yes, yeah. That will be the end of the Milky Way.
Right.
Uh,
But there is what will happen to Earth? When Earth might not even notice, probably won't notice.
When galaxies collide, they're mostly empty space. So stars basically wish past each other. And so people have calculated there's about a 10% chance that the sun will be ejected, right? It'll be one of the unlucky stars, it'll get a kick, and off it goes into intergalactic space. But the time scale we're talking about is now roughly 4 billion years. And on that time scale, that will be the sun approaching the end of its life. So on that kind of time scale, the Earth would already have become uninhabitable. That's going to happen in about 2 billion years. And then on the timescale of 4 to 5 billion years...
I thought it was going to happen in a few years.
Well, I'm talking about the astronomical end of the Earth,
Right.
rather than what we do to ourselves.
Right.
But on that timescale of 4 to 5 billion years, then the sun is going to change dramatically. It's going to stop being a small star. It's going to grow into a red giant star as it enters the last phase of its life, and its material then gets recycled into the next generation of stars.
All right, so we're safe from Andromeda.
Yeah, look, there are other things to worry about at the moment. We shouldn't worry about the collision with Andromeda.
All right. Well, thanks for the help. Well, I will clean it up, and then I'll call you back and show you, and we'll see the final version.
It sounds good. I'm looking forward to seeing it.